Well, thanks very much for coming. This is C++ WinRT and the future of C++ on Windows. My name is Kenny Kerr. Scott Jones is down here. He'll be helping me with some demos and chipping in other ways. And we are from the Windows team at Microsoft. This talk is inspired by a project that called C++ WinRT now. It started off as modern C++ for the Windows runtime. And it's all about bringing modern, idiomatic, and standard C++ to the Windows platform. So what's this talk about specifically? So one of the things we're doing is we're replacing proprietary extensions with standard C++ code, and we'll talk about what that means and practically how you'll see that today. Making Windows a great place for C++ developers. You know, for a long time it seemed as if Windows didn't really care that much, or that was the perception, and we want to make sure that that changes. Benefiting from advanced C++ 17 and TS features. So how we are internally using features in C++ 17 to really make our library development far simpler and far more efficient and elegant and so on. Even though the C++ WinRT library is very straightforward, there are no templates and there's nothing like that you need to deal with when you use it as a customer or a developer. And certainly internally we use a lot of these techniques internally to make it come alive, and so we'll show you some of those. Providing great tooling, and so Scott's going to give us a few demos of the tools that we've produced and how easy and elegant it is to use them to really get a lot of work done very simply. And then we'll show give you some idea of what's coming up next, and looking into the future, what we're working on in the longer term. So what is WinRT and C++ WinRT? So if you haven't really been following along, the Windows runtime is really made up of these three pillars: metadata, language projections, and the Windows ABI. So the metadata is essentially the compile time information. What does the Windows API look like? What are the classes and methods and so on? And language projections are the way that we project that into a specific language in a language-specific way. So what is natural for C# isn't natural for C++ developers or JavaScript developers as well. So a language projection is free to take the metadata and interpret it however they wish and make it work most elegantly and most efficiently with various trade-offs for a different language. The Windows ABI is often overlooked, but it's really essential because it's the thing that binds them all together at runtime. At runtime, we want to make sure that they can communicate across language projections, and it's really the part that the operating system has the most influence over, and certainly the contract that the Windows runtime defines. And so we'll talk a bit more about that as well. And C++ WinRT, simply the standard C++ language projection for the Windows runtime. It's a standard modern C++ library. It's a header-only library, so there's no runtime, there's no DLL, there's nothing you need to distribute. You just hash include and off you go. And it provides a classy type system. So this is not something like ATL or other libraries you might have seen from Microsoft before. This is really going to give you the first-class support for using the runtime classes that the operating system purports to provide, and you can call them in a standard way like you'd call any standard C++ library such as STL. So who's using C++ WinRT today? Obviously in Windows we're starting to use it quite a bit. Office has started using it in some of the applications. Adobe Photoshop today lights up on Windows 10 thanks to C++ WinRT, Spotify, and many, many others. It's a header-only library. We don't really know who all is using it, but certainly based on all the questions and the feedback we're getting, a lot of people have started adopting it, which is great to see. So from proprietary to standard, this is one of the big sort of themes of this library and certainly our emphasis in Windows in general. So one example is C++CX from the Visual C++ team. We're replacing that with C++ WinRT. You know, a bunch of language extensions in the compiler, do something that's written purely in C++ as a library. Another example is DeclSpec and UUIDOF, mainstays of COM development for decades now. We're replacing those with constexpr functions such as GUIDOV, which we'll talk about a little bit more as well. Another example is precompiled headers, so something that VC projects, Visual C++ projects have used for years, but has really reached the end of its lifetime in terms of what it can support, the scalability, rather inefficient solution, and we're really moving all our emphasis and all our investment to C++ modules. IDL in the middle, Microsoft-specific languages and tools and compilers that we'd love to move away from and focus more on standard C++ solutions. So how could we take a proprietary language and a proprietary compiler and replace it with standard C++ code as well? And then whatever compiles. If John Caves were here, I don't know if he is, he'd tell you about all the scary extensions to the compiler that we regret having put in the compiler in the first place, but he now has to maintain and support those because so much code is based on that. But we're moving to a world where we try to compile everything with permissive minus, which is a visual C++ flag that basically restricts the things you can do for the most part to conformant standard C++. And we also use Clang as a way to ensure that even further or greater standards compliance is reached by our libraries. So what does it look like? So here's a simple example. Imagine your manager says to you, go write a camera application on Windows. How on earth would you do that? So the Windows runtime makes that fairly straightforward, and C++ WinRT brings it to you quite concisely. So we start off using the storage library, a runtime class, to get the pictures folder. There's a save folder method. It's really a property called save folder, like return me the save folder, not save the folder. So it's a rather strange name, but let's go with that. You get back a storage folder object, which you can then call the create file async method on to create the actual file in that folder. So that gives you back a storage file object, and then you can prepare the webcam, setting up the drivers and whatever else is required. And finally, actually capture the image using that webcam or whatever camera is associated with it, and actually storing it in that file. So within one slide, thanks to coroutines and modern C++, we can condense an entire camera application onto a single slide. And it works really great. So what does it mean beyond just the library? So in previous talks, James McNeilton and I, we talked a lot about the library and its abstractions, how we project and surface the runtime in a way that's elegant and efficient for C++ developers on Windows. But we avoided talking about the tooling because we weren't ready to really reveal that. And that's what we're going to do today. So the way it works is you have this tool called CppWinRT.exe, and we call it a compiler because it converts from one thing to another. And you run it with a number of options. One is in, and local is one of our shortcuts, and Scott will be mentioning a few others. And what that does is it takes all the data in your system Win metadata folder and produces a set of header files that represent those APIs in modern C++. You can then simply hash include that into your C++ project and write your code and send it to your favorite compiler, Clang, CL, whatever you prefer. At this point, the tooling that we provided is out of the way. You no longer have to deal with it whatsoever. And now Scott's going to come in here and give us a demo.
Can everyone see a console behind me?
Yes.
So far, so good. Okay, so the first question you might have is, where is CppWinRT? Well, it's in the SDK, or it soon will be. Next month, when we ship our first RS4 SDK, after we ship RS3, we expect to unveil the tool, CppWinRT, the executable, as well as a projection for the SDK. So it will be a first-class experience within the console. This is a developer console. Within Visual Studio, within VS Code, within any of the tools that Microsoft supports. Let's take a look at what the options are for the tool. Okay. Just a handful, really. We've got, as Kenny demonstrated on the slide, we have a -in option. So this is how I specify the source metadata, the WinMD files. It could be a file path, could be a single WinMD file. We've got a couple of mnemonics down here for the SDK. I can say, give me the current SDK that's installed. And optionally, with the plus, I can say, include any of the extension SDKs. Or I can say, give me a specific version of the Windows SDK that's installed. If it can't find it, it'll error out. Or I can say, give me the local Windows System 32 Win metadata content. Typically, you wouldn't want to do that. Usually, you want to, if you're going to create a projection, you want to control the version that you're using. But it really is more or less as simple as that. We have references for WinMDs. If we're building a projection that's based upon another projection, then we need to specify the reference to that other projection upon which we depend. And the reason for that is because just in the same way that WinMD files can reference other WinMD files, well, the projected headers have a similar dependency. And so that's how we would achieve that. And then finally, we have an out parameter here. And this tells us where we put the projection. Okay, so let's go ahead and build a very simple projection. We'll just say, give us the local Windows System 32 Win metadata content and create a projection for it and put it in a folder called out. And in the time that it takes me to type that and run it, I now have a projection. So if I take a look at what's in that folder, I have 280 some top-level namespace headers. Each one of these is a self-contained namespace header generated from the WinMD file and contains the runtime classes and the machinery needed to instantiate those from a consuming perspective, as well as from a producing perspective. So let's take a look at how easy it is to create a consuming application using CPP WinRT, using a projection. The first line I'm going to type is not standard C++, but bear with me. This is just so that I don't have to create a project file. Windows app is an umbrella library that provides all of the Windows runtime free functions, the entry points, and the functions upon which the projection depends, is implemented. The next thing I'll do is I will include a sample top-level namespace. Windows System Diagnostics. What we're going to do is diagnostics.h. We're going to consume the System Diagnostic Info class, which the browser is implemented in terms of. So the F12 debugging, if you've ever used that, then we're going to reuse that component, okay? Using namespace WinRT, that's the top level namespace for the Windows runtime. And this provides entry points like init apartment and make template functions and that sort of thing. And then for the specific namespace that we're going to consume, diagnostics. We'll type that in. And then we just simply init our apartment. This is an abstraction, an exception-friendly or exception-enabled abstraction around the row initialize call. And now we can just instantiate the Windows System Diagnostics. System Diagnostic Info. Get for current system. There it is. And in a very natural, intuitive way, I've got access to the static factory method, get for current system, which will instantiate the System Diagnostic Info. All right. Now with that, we will access the memory usage property. Having a little bit of trouble with the IntelliSense today. Upon which we will dot in and access the report property on that. And then finally we will access the total physical bytes. I want all of that.
We're still teaching the IntelliSense engine to not think that we're the Windows ABI.
Yes, we're getting a little bit of interference, but that's okay. All right, so on the info object, I've accessed the memory usage property. It's pulling back an object, a temporary, upon which I am then invoking the get report method. And then from that, I'm pulling back the total physical size in bytes. All right? And then we'll just simply print that out. Okay. Now, before I compile this and run it, I'd like to just call your attention very quickly to what would this code have looked like if I had used the Windows resource, the Windows runtime library, all right, which is the other alternative that you had up until C++ WinRT for creating a native ISO C++ client code for WinRT. If you didn't want to use CX, then this is what you had to deal with. Well, as you see here, we start off with some sort of machinery, macro machinery for dealing with H results, because those are front and center. Everything, every property access or every method that you call is returning an H result. And so you see how that begins to clutter and dominate the code, the landscape. I have to declare local, temporary, for the System Diagnostic Info statics. This is just to construct the thing. And then I have to supply a runtime string for the runtime class. Where am I going to get that? Well, I simply scroll down to line 2789. I have a convenient string definition for that runtime class. Okay,
Handy.
so I need to know where to find that. And then I supply that to the getActivationFactory. That provides me a static factory method, upon which I can call getForCurrentSystem, saving the result into a local, a temporary. Well, I'd like it to be a temporary, but it's not. It's a named. And then returning out once again. You see how ponderous and clumsy this is, and how it really gets in the way of a fluent, chained, dotted style of programming, which was really what I'd like. I'd like to focus on the domain and not on all this other machinery, right? So that is what this natural modern C++ projection affords, okay? All right, well, let's go ahead and build this. I'm gonna build this with Clang, the latest distribution of Clang, which supports end-to-end compilation and linking of a Windows executable, as well as PDB file generation. And the only reason I'm doing this is just to demonstrate that this is standard C++. I can do it with Clang, right? There's no tricks. To Kenny's point, I'm not using all sorts of compiler and extensions that are Microsoft specific. And then finally, I'll go ahead and run the program. And there I have it. So in just 2 lines of code, effectively, 2 lines of user code, I'm able to hash include, create an instance, dot in, and there we have it. Back to you, Kenny.
Thank you, Scott. There we go. All right, so let's now talk about, going wrong way. Went backwards there for a moment. Benefiting from C++ 17. There we go. So this is CppCon. You've probably been here all week and seen many ways where you can benefit from C++ 17 in many different ways. I want to give you some concrete examples of how we're doing that within Windows, within this library, to solve real problems. If you're perhaps curious, there's some significant savings we've seen over the last 2 years as we've picked up more and more of those features. One example, a simple example, is nested namespace definitions. We picked this up early on. It really turns this rather verbose code into something really a lot more elegant. You know, we use a lot of namespaces and types in the Windows runtime, and this makes our life a lot simpler. It just makes the code a lot more beautiful to look at and use. And then when you get to the authoring experience as well, the code that you have to deal with and are confronted with is also a lot more concise. Perhaps a more practical example is this one from ComArray. So the Windows runtime inherited the allocator from Com, which there was basically an alloc and a free function similar to the C runtime, and it's called code_toss_mem_alloc and code_toss_mem_free. And the Windows runtime uses that to establish an ABI portable array type, which is used in some cases, not all. And the challenge is with C++ 03, you have to deal with this concept of, well, what kind of value type or what kind of type am I actually storing in this COM array? And so you might have this class template, and before freeing it, you actually naturally want to call the destructors on your types. The challenge is what if T doesn't have a destructor? What if it's an integer? Then this won't compile. And so you're forced to use various less than ideal solutions. You might have a complete specialization, a partial specialization for different types, but it gets really uncomfortable and awkward very quickly. C++ 11 gave us a better solution. So we can use type traits. You can say, well, is the value type trivially destructible? In which case, we don't have to call this destructor, and we can simply do nothing. So we can basically do type switching with these destroy overloads, and do that if it's trivially destructible, or call the destructors if it's not. And this is great because the compiler sees that that's within a class template. It'll not actually compile that code or attempt to compile that code in such specializations. C++ 17, however, does much better, and it says, well, let me just take care of all of that for you, and we can call std_destroy, and it does all of the same machinery behind the scenes, and again, compiles away to nothing if T happens to be some type which is trivially destructible. And this actually avoids a Visual C++ compiler bug, a codegen bug, which I found while preparing the slides, but I'll save you the details there. Another way we take advantage of C++ 17 is with logical operator traits. So this is an example of an implementation. So you can naturally implement the iStringable and the iClosable interfaces for yourself, for your own implementation. And we'll take care of doing all the machinery behind the scenes that's also required by the Windows runtime in some cases. Some examples include implementing IUnknown, reference counting in QI, IInspectable, IAgileObject, and IMarshal, and others. So how do we know when to implement these interfaces and how to implement them? And so that's where the logical operator traits comes in. We want to answer those kinds of questions. For example, we want to know, is this an agile implementation? Should I be implementing the IAgileObject interface? Now, absolutely always be agile, but there are cases when you might say, no, I need this to not be agile. And so we have this non-agile opt-out mechanism. It's a marker type you can just stick in there, or here, or anywhere else in the variadic parameter pack to say, no, back away, don't implement that for me, I'll take care of this myself. So we need a clever way of saying, well, how do we detect that at compile time? And that's where the logical operator traits comes in. First up, we say, well, is I really non-agile, as in it's not an interface? And then we use disjunction to say, are any of the interfaces or any of the types here non-agile? And finally, we use stood negation to say, well, that's the result of the isAgile type alias that we actually care about. And so we take a lot of complex reasoning and we stick it in a type alias that we can reuse. A few more examples: is factory, is inspectable, and is weak reference source. Just more examples we use inside the implementation to make those sort of deterministic decisions at compile time and to save you the work of having to figure that out. And we also do things like doing static assert on these, so we make sure that you cannot actually produce an invalid implementation without getting a compiler error. And that's just essentially what we're expressing there in that last type alias. Another example of how we've really benefited from C++17 is this example here. So within a query interface implementation, this is a runtime method. It's kind of like dynamic cast. The caller would say, well, given this GUID representing some interface, please go ahead and give me your implementation if you have one. And so we need to first figure out, well, how do we implement this based on a variadic parameter pack? So one method is to say, use Sphene. So we say, for this function template, we'll only match this one or allow it to be used by the compiler's decision making if first is an interface. And if so, then we might compare the GUID and possibly return the v-pointer. Otherwise, we'll keep looking. But now we need to go to somewhere else, some other function to do the rest of the work. So we have another function, another overload, another function template, which does the inverse. Well, it says if first is not an interface, and then we'll just keep looking. So here we're essentially just skipping over that first type parameter, and all of this code needs to be written just to do that simple skip over. And finally, we have the terminal case. We need to say, well, we've run out of type parameters. Let's go look elsewhere. Perhaps there's a base type which we get more functionality from. Well, we have this weird template machinery we have to deal with, which is awkward. It works, but it's a pain. Wouldn't it be nice to take those three functions and stick them into one? And that's exactly what we do with ifconst_expr. Here we can sit and essentially say, forget about Sphene, and we start at the top, is first an interface. It's a compile time expression, so we can do that. We then say, well, if it has a matching GUID, then we can return the v-pointer. Otherwise, if there are more type parameters, we can keep looking. Because it might even be that, even though the first was an interface, it might not have been the one you wanted. And finally, we can look elsewhere if there's a need for that in terms of a composable hierarchy. But the point is, we've taken all of that code, which tends to get spread out across a large header, and stuck it in one place that's easy to reason about and certainly far simpler to write. So another example of how the Windows operating system has made life difficult for C++ developers is with GUIDs. So we have these GUIDs that are associated with interfaces, and we've added these extensions for years where you can associate that GUID with that interface, iStringable, and then you can look it up later on with the UUID of keyword. And the way this works is essentially a caller in the main function might say, I'm looking for this interface. It gets passed to the implementation, which does the check and possibly returns it using that out parameter. So that works as well as it does, and we could probably live with that. But then the Windows runtime came along and made it really, really complicated. What is the GUID for the iVector interface? Well, the problem is that it could be one thing if it's an iVector of int, or it could be another if it's an iVector of a string. It gets very, very difficult, and we have a complicated way of working that out, but they have to be unique. So before, what we did is this, essentially. We had a static assert which would simply fail, and if the specialization wasn't found, as in it wasn't in metadata and we didn't emit the specialization for you, this is the bailout. This is what you would get. And essentially it boils down to good luck trying to figure out what the value should be. We didn't include that in the shipping version, but that's essentially what we were saying. So we've replaced all of that with a const expr function. We literally have all of those extensions are gone, all the static assert is gone, and we've baked it all into the base header. So you can look at all the code, and you can now simply call the GUID of const expr function, and to get the value out that you need. And it works with whatever crazy container of maps and maps of containers you could imagine. It does the work of figuring that out. Now, how does that work? Well, I'm going to spare you all that code because it's non-trivial, but essentially it boils down to this. So we have these type traits. So we have the full specialization for the iStringable. Now we know that GUID because it's in metadata, so we just roll it out. But for generic interfaces like iVector and IMAP and so on, we have a partial specialization. And in there we essentially have a const expr function which does what that RFC says you should do. We generate a string given the specialization that you pass in, so we actually build that string dynamically at compile time. We create a buffer with a certain given starting GUID and the UTF-8 representation of that string that we just created. We then have to hash it and grab the first 16 bytes of that hash. We then convert that to a GUID. Those 16 bytes essentially become the GUID. And then we have to turn it back into little endian because we're Windows and do a bit more twiddling, and then finally you get the value out. But you get that value out at compile time, which is incredible, and all that pain, really the biggest problem we had with developers using our projection simply goes away, thanks to const expr functions. And there's many, many more ways we're benefiting from it. We use std optional, std variant, my two favorites. We have string view, and Scott James even highlighted, lighted up for us deprecated. So the Windows API has a number of deprecated APIs. We now translate that into using the standard deprecated attributes so that you'll get a compiler warning or error saying, hey, you should use this other API instead. For example, we have some unique requirements around code injection, and we use has include, another standard feature. This is not a compiler extension, even though it looks like one. And then coroutines. We use coroutines heavily, but James and we chatted about that a lot last year, so I won't get too much into that. There are things that we haven't started using because we're waiting for the compiler. So Visual C++ will soon give us fold expressions and tablet argument deduction, which would make our headers even simpler still. So I'm looking forward to those as well. So I know a lot of you have asked me questions this week about developing components. And so we'll talk about that now. So developing components is largely the same in terms of how our tooling works. You simply call that same CPP WinRT executable that Scott demoed for us. There's a dash component option which lights up the component authoring experience. Now this is not a different projection that it produces. It's rather a superset of the projection you would get if you were otherwise consuming those types. But it includes a Visual C++ project, a module.def file, and the various scaffolding you need to actually author your own types. Now again, this is not Visual C++ or Visual Studio specific, but we do make it very easy for you because a lot of developers we know want to use Visual Studio for their component authoring. And that does give us things like round tripping. When you're updating your metadata, we update the scaffolding below, underneath the covers for you automatically, which saves a lot of time. And now Scott's going to come up and give us a demo.
Okay, so there are two sides to every ABI. There's the consuming side and the producing side. We've already seen how easy it is to create an application that can consume a WinRT component, the system diagnostic info. Let's see how easy it is to actually implement that same component. So returning to our, we call it a compiler. I don't know why. We could call it a projector too. It's a funny name, compiler.
It converts
We're
from
always
one thing to
confusing
another.
ourselves. Let's take a look at the third demo here, the third sample, which coincidentally is exactly the command line I need for this demo. So it's very, very handy. So let's take a look at this. We've got CPP WinRT -v. I'm using the single letter abbreviations here for the options. -v, give me verbose output. -c, generate the component scaffolding that Kenny just mentioned. -r, reference WinMD files from the current SDK that's installed. -n, use this as the base name for the module that I'm putting together. This will in turn drive the name of the output binary, the DLL. -f, filter all of the fully qualified type names that I want included into my component to those that begin with this string, windows.system.diagnostics.system. Okay? And then finally out, create the projection in a WSD folder. We'll go ahead and run that, and you can see 350 milliseconds. I now have my project scaffolding. Let's see what that looks like. Okay, we see the module level. This module.cpp includes module locking mechanisms and activation factory and that sort of thing. We've got a precompiled header, and then we've got this trio of files for each one of the top level, the runtime classes that the component implements. We've got a .g.h. This is a template scaffolding that provides both a runtime class, base class template, as well as factory implementation if you have that for your runtime class. And then we've got user-defined header and CPP, and that's where we'll turn our attention as we implement. So let's go ahead and open up that generated project. Okay, so just from a usability perspective, we decided to throw all of the generated scaffolding into a generated filter folder, so we don't have to be bothered with it most of the time. Let's return our attention to the consuming application that we just created. Now we have 4 WinRuntime functions that we're calling. There's a static creation method, which gives us back a system diagnostic info. There's the memory usage property accessor. There's a get report method, and then there's a total physical size and bytes property accessor. So 4 methods need to be implemented. All right. So let's start at the top and work our way down. System diagnostic info. Let's go in there. Okay, right down at the bottom here is where our get for current system static method is. All right. So apologize for the scrolling, but all right. Now, in order to create one of these, I will use the make template method. And what this does is it will instantiate the derived type, and then it will unroll the underlying ABI pointer and create a smart pointer that wraps that and returns that out. So very, very simple to use there. And then in turn, we're going to call the memory usage property accessor and generate for ourselves a system memory usage. So I'll do the same thing there. Now this is a property. Generally speaking, we would probably have this thing persisting as a member, but in this case, I'm just going to new one up. And immediately I get a red squiggly under make, and the reason for that is because I've just hopped tracks to another namespace header, so I need to make sure that I include that. Okay. Now I've implemented my system diagnostic info class and its memory usage property accessor. Let's move on to the memory usage class. And we see the same pattern repeated. In this case, we're going to implement get report. And similarly, I need to hash include that header. All right. And finally, we'll jump down into the report. And just to make it clear that we're implementing this property, we'll return a fixed value. Okay. And then the only other thing I need to do at this point is address my constructors. The compiler has been a little careful on our behalf, conservative, and has deleted all the default constructors because activation, which is the WinRT word for construction, should be something that we explicitly control. So we'll just go ahead and opt those back in. Start with the system diagnostic info, moving on to the memory usage. And finally, the report. Okay, I'm going to return back to the report source and drop a breakpoint in here before we move on. We'll go ahead and build it. First thing we see is that there's a whole bunch of spew here where I see ref out SDK. That's the CPP WinRT projector compiler executing once again. That's been baked into the project scaffolding that we created. And the reason for that is because if I had started with an idle file, or if I was concerned at all about the input Win metadata having changed, I want to make sure there's a dependency, because that's what I've generated my component scaffolding off of. And so we've got that built in as a custom build rule. Looks like everything built. So let's go ahead and copy the generated binary into our Windows system 64, 32, wow, location. All right, and then we can execute. Oh, but first...
you must be an OS developer.
I must be. Let's set for ourselves a debugging application of the application that we just created. CppCon show mem.exe. So we'll use that to drive, since this is an in-proc component, a DLL, we need an executable to load the thing up. So we'll just use the program that we just created. And we'll run. And it hits our breakpoint. Let's take a look at the call stack. Apologize for the font size, but we can see from the call stack that we've got 2 levels in show main for our client application. And I'll just call your attention again to the fact that we're using PDBs that are generated both from Clang and from Visual C++. And these are very neatly stitched together into this unified call stack. So that's kind of neat. And then we've got 2 frames as well from the component itself, Windows System Diagnostics. So let's pop back up here and let's work our way out. I just popped out of that top frame. And we can see here that we are now in the wrapper, the shimming that shims up, right, in the component itself, shimming up from the ABI layer to the implementation of the property or method accessor, okay? And let's keep going. And very lightweight, as you can see here, very thin C++ wrapper that compiles away to nothing. And then we pop back out. Now we're back into the consuming side and the inverse, the symmetric inverse of that, which is the shimming down to the ABI on the consuming side. That's all that you're seeing. You've seen 2 functions with 3 lines, all of which are inlined. And out we go. And we print our output 42. So it's that easy to implement components now with C++ WinRT.
Thank you, Scott. Yeah, that was a good demo. All right. Awesome. Okay, well, so what's coming soon? What's coming next? What can you expect? So if you work at Microsoft on the Windows operating system, you can look forward to the Windows build being updated with a compiler that supports building using this library. We've had some trouble up till now because the compiler is slightly behind what you have publicly with Visual C++, and it doesn't support all the const export things we need to actually make this work. And so that'll be available fairly shortly, I think in the next week or 2. Windows SDK for everyone else at Microsoft and around the world, you get to access this through the Windows SDK, as Scott mentioned, pretty soon, I think in the next few weeks. Whenever the first RS4 SDK comes around, you'll have access to those bits and the headers, and it'll all just work as you've seen Scott demonstrate. The XAML compiler is something a lot of people have asked for, or even if they didn't ask for it, it's what they imply when they say we want full XAML support. It's something that sort of straddles Visual Studio and the Windows operating system, and it does all the language-specific code gen within Visual Studio, and that team is now actively working on doing the code gen for C++ as we speak, and so that will be working fairly soon. And then what we need finally is Visual Studio to bring it all together and give you that file new project experience that everybody enjoys. So that's all coming, finally sort of coming together really well, which has been great to see. Then looking into the future, I want to talk a little bit about what we're planning to do in the future. You know, what are the ideas and the things that we're investing in, because certainly the work isn't done yet. We have a lot more to do. And you know, one of the things Scott mentioned is, well, is it a compiler or is it something else? Well, I'd love for it to be nothing, and I'll tell you why. But first, I want to mention something that's really important to me and important to the success of modern C++ in general, which is the optimizer. Making sure that we can train the optimizer to really do the best possible job with modern C++ code Otherwise, there's this whole class of developers we're leaving behind, developers that really need the perf that we need to give them. So one of the big things for us, and that I've demonstrated already, and last year as well, we talked about this, is using modern C++ techniques, even within our implementation, to reduce the complexity of our internals, reduce the complexity of our implementation, such that with every version of C++ WinRT, the projection itself has actually gotten smaller and simpler and more concise and more to the point. What that means also, it helps in a number of ways. One of the things we've done is moved a lot of our code to const_expr, which actually has a great benefit for binary size, because there's so much more data that can actually be stored in a more efficient way by the compiler. We also reduced instruction count. Ryan, who's over there, is on our team, and he did a number of great optimizations to reduce the size of the instructions that are actually laid out on disk for the implementation of certain very high traffic calls, such as string input parameters. And that's been great to see how those optimizations can be tightly controlled and make a big impact on large-scale components. We have internal teams like XAML who are using this now for their implementations of their own DLLs, and at that scale, when you have a DLL that's 15 megs, it's a pretty big deal when you can save a few bytes on every instruction or on every API call. Inline all the things. So when you get to modern C++, you're talking about constructors and what is effectively a property, something that returns a value directly rather than as an out parameter. Those things that we return and we create, all the temporaries that you saw in Scott's demo, they all tend to be objects with non-trivial destructors. And the trouble is the Visual C++ compiler has for decades not been able to inline those things, those types of objects. So you have a function returning a non-trivial destructor, or returning a type with a non-trivial destructor. You cannot inline that function. You have a function with a try-catch block, it's not going to get inlined. Thankfully, that now was enabled with the compiler switch first, and now it's on by default in 15.3, which is immense for our library and libraries like this, for SDL, things like that. Because the compiler finally has the far greater ability to inline and optimize and make good decisions about how you want to optimize your code, whether it's for size or speed or somewhere in the middle. And really what that comes down to is talking semantics with the compiler, saying to the compiler more about what you're trying to achieve. Scott's demo showed 2 lines of code which really concisely expressed what he was trying to do rather than how he was trying to do it. Whereas the world code, the ATL style, H results and pointers, it didn't really tell the compiler anything. Now, thankfully, most C++ compilers today are optimized for C code. So that's great for that code, but what we want to do is make sure that C++ compilers today and the optimizers they come with are really geared towards optimizing modern C++ libraries so that we don't have to compromise our designs in order to get the best possible performance. Const_expr for all the things, I've already talked about that. So much benefit there for us to put more and more work into the compiler at compile time. And exceptions. So much of the design we have today with libraries presupposes that you're using exception handling, or at least that you're using exceptions as a way to report errors. Now, you might write an application using a library like this and never have a catch block, and that's perfectly fine. But when something exceptional happens, it's going to get you out of there and crash your application. You might get a crash dump from Microsoft or from your own server, and you'll have the data you need to really track that down. The trouble comes when you're the operating system or you're a component and you need to cross an ABI boundary. At some point you hit an ABI boundary, like you're implementing one of those methods that Scott implemented in his demo, and something goes wrong and you need to throw an exception. At some point you hit that ABI boundary and you need to stop. You cannot have that exception propagate, that's not going to work. And so you need to turn that into an H result or something that the ABI can convert into something that another language projection or another compiler, another toolchain can convert into their own form of error handling. And the problem is that catch block is what's expensive. That's where a lot of our code load comes from today in our compilers. And so we're working with a C++ team to give them those kind of repros, because we can create a component with thousands and thousands of ABIs, of methods that might catch and throw exceptions very quickly. And so we have the ability to give the compiler team these incredible repros that they can then use to optimize modern C++ code. And this is something we're actively pursuing today. So that's a big deal, and I'm hopeful to see even more, even as the compiler has done immense work to optimize for modern C++ over the last 2 years, we're going to see even more in the coming years. So, 2 more things I want to talk about. One is C++ modules. Now, C++ modules, I mentioned it briefly. Why does this matter? So today, as we illustrated already, we have this model where we have this Win metadata folder or some other set of WinMDs, and we pass it to our CPP WinRT compiler as an input. And as an output, it produces these headers. And you saw that live, so it works, and it's great. You know, you get headers, and they're standard C++, and you can simply hash include them. So what's wrong with headers? Well, there's lots of them. There's over 1,000 headers. Earlier versions of the projection had even more, close to 2,000. So we've condensed them down, but there's still a lot of headers. Roughly 1,032 at this point. That amounts to about 40 megs worth of headers of source code that the compiler needs to parse. And that takes a long time. And when you're building a simple console app, like that camera application, that's not a big deal, but when you're using some of the larger namespaces, like the XAML namespaces, they're very big, and it can take 30 seconds or a minute sometimes even to just compile those headers up front. So precompiled headers are not the solution. They're huge. The problem with precompiled headers is that they essentially take the layout of that type information in memory and just write it out to disk. So you can easily land up with enormous PCH files, which are unwieldy and take a lot of space. They're not efficient. And it causes other troubles as well. They're not reusable, for one. So you have a Visual Studio solution with a number of projects. You cannot share the PCH. Now, there are some hacks I've seen people do, but it doesn't work well. And they don't offer isolation. So you have your header-only library, and you've got macros in there, perhaps, hopefully not, but perhaps. You have some implementation namespaces where you're doing some internals, and you'd like to rev that and change that from one version to the next. But all of that leaks out, so app developers can take advantage of those things, and it really causes trouble for you and for them because of that. And finally, 40 megs of headers, big compile time, all of that memory layout, that's going to hurt your machine. You're going to often have to use the big object flag with Visual C++. In many cases, Clang won't even compile our headers. If I include every single header that we have, the Clang compiler will not compile it. It runs out of memory. And Visual C++ handles it. They know me well now, but but you often have to use the cross compiler, which means you use a 64-bit compiler to compile 32-bit code because you have a bigger address space, and that works great. But some people can't use that. The last time I checked, the Windows operating system cannot be built with a cross compiler because they don't have enough memory, or it takes too long, or something like that. Someone could correct me, but that's what I heard. So it doesn't scale. As a more visual example, here you have the includes up front there. So that's how you do it today, and that amounts to between 1 and 3 gigabytes of a PCH. It's very error prone as well. So you've just done that, but those namespaces might include declarations of types, but not their definitions. And we do that because we're trying to avoid creating big PCH files. But the problem is you'll get a linker error saying, well, you've used some type and there's no definition, and you get this cryptic linker error that says something about namespaces and stuff that I don't recognize. And so the solution is just you've missed a namespace, go and include it. But I'd love for that problem just to go away because it's really weird. And the final issue with this is it's rather redundant. You've named all the namespaces at the top, you name them again at the bottom because those are the ones you actually want to use, and it gets real tedious pretty quick in a large application. With C++ modules, all of that goes away because you don't need PCH files. You simply import WinRT. Because it's so concise and so efficient, you don't actually have to have a WinRT module per namespace. You can just have it for the entire Windows API. Now, perhaps XAML gets enormous in the future, and we might have a WinRT.xaml just for them, similar to the way that the standard libraries are, creating subsets of names of modules. But it eliminates all the linker errors. There's no redundancy. You just declare the namespaces that you'd like to actually use. There's macro isolation. And so the way we define the module for C++ WinRT, we can specifically say this section of types or functions within this namespace is going to be exported, and the rest won't be exported. So we can easily hide all of our implementation details. Our implementation namespaces are all internal to us. And finally, because the module format is the binary format, it dramatically improves IntelliSense. So IntelliSense works reasonably well in Visual Studio today. They've been testing our library for quite a while now. VS Code, as you saw, doesn't work that well. They haven't caught up yet, and it's not a great story there. But with modules, we're essentially saying, don't worry about parsing my code. I mean, what Visual Studio does is that it literally reparses all your code with a different compiler and then produces that experience that we all love. But it's not a very efficient story. With this, it will be much more efficient. And we get dramatically better build times as well. All right. So reflection, code injection, and meta classes. So this is looking more into the future. So no doubt you've heard about static reflection and code injection this week. And during Herb's talk on meta classes, he mentioned a number of these things. And this is something we're pursuing, and we've been working with Herb Sutter for quite some time now to make sure that what will eventually become a standard is rich enough and expressive enough to deal with what we're trying to do. So halfway through Herb's talk, this pops up on my phone. So when are we going to see C++ WinRT implemented as a const expr WinMD parser and a set of metadata classes or meta classes? And this is James McNellis, and he was my co-presenter last year at CppCon. So it was quite surprising, not that surprising, but it's kind of funny because I didn't prompt this, I didn't pay money. This was just a random comment, absolutely. The interesting thing is that this is actually what we're thinking of doing. So it is very interesting. So to begin with, we know today we have consuming metadata. This is a basic scenario that we have. You start off with metadata files, WinMD files. You stick them through our compiler, and you produce a set of standard C++ source files. The producing side is a little bit more questionable. Now, we have good tooling, and Scott demonstrated this, so it does work. But the question is, starting with standard C++ code, how do we get to the results we really need? We send our C++ code through a compiler, Clang or Visual C++, and we get that executable. But how do we get the WinMD? And that's the challenge. So today we have a slightly complicated story. So you might start with IDL, a project.idl file, which is that proprietary language that I mentioned. And we then stick that through the middle compiler to produce a WinMD. And then we have to feed that all the way around back into our compiler to produce the scaffolding or update the scaffolding that we used to then actually compile the application with C++ or standard C++ at that point. Now this is obviously not a great scenario. You don't want to see an architecture diagram like this. That would be a really bad idea if you were to come up with this at a meeting, but this is actually what we do. This is the state in which we've evolved our platform, and we're working very hard to come up with a better solution. And one of the tools that we're going to use for solving this problem is meta classes and reflection and all these things. And what that essentially allows us to do is define everything, both our consumption story as well as our production story, inside C++. So you can imagine that read metadata and write metadata are const expr functions. Now, read metadata might literally go and find files at compile time, load up the file, parse the metadata, just as James was saying. And you might also define, the project itself might also define additional types, runtime classes, and so on, APIs. It might even use those types that it imported as part of its implementation. And then finally, it would write out the metadata to a file again. Again, those are both const expr functions. They both happen at compile time. So it's really not, so at the end of the day, you end up with an executable and a WinMD file, but it's really not the compiler that's producing the WinMD file. Like with C++CX, it was literally Visual C++ doing that. But today it's literally your compile time const expr code that does that for you. Or not today, in the future, if we manage to get this to work. So this is where we're going with that story. This is the kind of things we're thinking of. There's a lot of hand waving here. I mean, the meta classes work that Herb Sutter's invested in, and Andrew Sutton, if you saw his talk, the code he's written in that prototype compiler for Clang actually works, and it's incredible to see it. You can see it on the Compiler Explorer. There's even a page there where you can try it out. But it's still far in the future, so this is what we're planning to do, or at least what we're investing in to see how far we can take this to make a great experience for C++ on Windows. Just as an example, here's what we might imagine to see a number of meta classes for the Windows runtime. And as Herb was saying, this is how we would define the constraints or the defaults for those types to categorize them more clearly in a way that we can then use static reflection to say, well, this is a property, this is a method. These are all the things that we can unambiguously define and identify in your source code, which we cannot do today, but in a way that we can then clearly produce metadata from those artifacts. So what might an implementation look like? Well, here's a rectangle interface. So WinRT has interfaces and classes. This is just a class, but it's a meta class. It's based on a meta class, and so we can use the compiler to give us the declarations for those things, and then we can go even further and say, well, here's both the declaration and a definition. The compiler, through meta classes and static reflection, can take this, fold it into the number of projections that we need. So if you think of C++ WinRT as a projection, that's true, But under the covers, we create a number of things. We create an ABI, so a production experience. We create, with the vtables and all those things that you might program against internally. We create a production side and a consuming side. Those are the shims that Scott was mentioning in his demo. All of those things need to be, all of those artifacts need to be created at some point, and we can use meta classes to produce them with code injection and static reflection to figure out what to produce. Now, finally, I want to just mention, if we have time, that it's not just about saying, C++ needs to improve because we have this great Windows platform and we're just waiting for you guys to catch up. We're also trying to see what we can do in the platform itself to bring the platform forward, make a richer, more programmable platform that we can serve the needs of the C++ compilers and tools and especially the high performance needs of certain teams. So one of the things that we're imagining we could do, for example, is look at the ABI for the Windows runtime. So today this is all hidden inside the projection. You don't see any of this. But the reality is that the button class, let's say you have a button class and you have this iButton interface. It starts off by, the root interface is obviously query IUnknown, and it has 3 methods. Then there's IInspectable with 3 methods. And then finally you tack on the end whatever is specific to your interface. So if your button implements iButton and iStringable, those are 2 different vtables with all of those methods. And then on the left, you see what's essentially your instance. Your instance has 2 VF pointers, and this is a runtime cost. This impacts the size of your object in memory. Now you might, in a second version, add a second interface. You want to add some more functionality like a color property, and even a third. But as you do this, you see that the instance size grows. And so that's a problem for implementers. Certainly with large APIs, this is going to quickly become a real problem in terms of their implementation getting more and more expensive over time. Now the solution, if you've developed COM applications for years, might be obvious to you. Interface inheritance. We've had this for years, it's been around forever. Button 3 derives from iButton 2. iButton 2, there we go, derives from iButton. This is not a shocking revelation here. Every person I've talked to about, the problem, they immediately jump to the solution. This is clear that this is something that would immensely help us from an efficiency perspective. So we're looking at how we can do that. But it's not only an issue for component authors. Application, sorry. Okay, there we go. So this is essentially just another view of the same thing. So button 3 derives from iButton 2, which derives from iButton. What that means is that iButton 3 is a superset of iButton 2, which is a superset of iButton. So from efficiency perspective, this is ideal. You've been able to condense the VF pointers. There's only one VF pointer for the latest version. There's a VF pointer for any other polymorphic interfaces that you might want to implement. And then all of the actual interesting implementation details for your component or for your runtime class are condensed into a single flat list. Now, as I was trying to say, this isn't only a benefit to component authors, this is a big deal for applications as well. Teams like Office come to me and say, well, calling these WinRT APIs is rather expensive. What can we do about it? Well, why do they say that? Well, let's imagine you have a button class. You've just created that object on the stack. Internally, it holds an iButton interface pointer. You want to set the text property? No problem. That's a virtual function call to the putText virtual function. Now you want to set the color property. Sure. C++ WinRT does it for you, but it has to inject a call to query interface to get the appropriate vtable in order to make the second call to put color, because that's a different interface. Rotate is much the same, and so is query interface. The trouble here is obviously all these additional calls, and let's not forget about all the release calls at the end. All of that fills up your binary. It's more code to execute. If you were in the Godbolt talk, you would have seen all that machine code, nanoseconds worth of stuff he's mincing over. This is dramatically more. This is a lot of CPU cycles doing all those virtual functions. As grows your binaries, this can be a big problem depending on the scale of your application. With a streamlined ABI, this gets far more straightforward as you can imagine. In this case, we're holding onto iButton 3. This is the virtual function call. So is this and this. There's no other overhead here whatsoever. This one actually is still a polymorphic interface, which anyone can implement, so we QI for that as before. But we've reduced a lot of the instructions in the implementation, and we've done it in a dramatic way, which saves not only the component author and the application's address space, we've also saved code on disk, made your code far more efficient. So these are just some of the things we're thinking of doing, we're dreaming about, we're trying to see how we can move the platform forward as well as the C++ compiler. to make this world where C++ developers really love using Windows. And thank you very much. You can download it today. You can learn more over there, and you can follow me. And thank you. So if you have any questions, feel free, and we'll be here afterwards to take them as well. We answered all the questions. Hi.
Hi. I got two of them actually, completely unrelated. The first one is you've shown that the errors are sent by exception in the components, but on the client side, I saw that you use a lot of dot operators. So how do our errors handled if any of that calls failed?
Sure, that's a great question. So again, this all comes down to the ABI. So within the implementation, you use modern C++ and you throw exceptions for errors to propagate up. But when they hit that ABI, we essentially have a catch ... which takes that exception and turns it into an appropriate H result. It also does things for the debugger to be able to light up with stack information and a bunch of other things that we need for error origination in the platform. And then it simply returns the H result, which is the error code that represents that exception. The language rejection on the consuming side then resurrects that exception and rethrows it. So it takes the error information, turns it into an exception again, and just calls throw on that. So it's as if you threw from one side to the other, but it went through this ABI. So it could be one compiler and another, and it still just works.
Yeah, I can certainly see the point. My other question, I really like the fact that you try your first demo with Clang. That was very cool. But my question is, if we go for modules, since it's clearly not stated if the binary for the modules will be the same between compilers, well, how will it work between VC and Clang if it's not specified anywhere?
Sure, that's a great question for the compiler teams. We're just consumers like you. We write libraries like you. We're not specifically involved in the generation or even the definition of the module specification. My understanding today is that it's compiler specific. So you get an OBJ file, you get a binary, but they may not work across different compilers. But it is great for a scenario where, let's say you're building Windows and you have thousands and thousands of projects, and you don't want to recompile all of those things. You could have within that sort of contained environment one module that defines those sets of things that you're reusing, and you can have immense savings. And even if you have a Visual Studio project with a number of projects in it, a solution with a number of projects in it, you're going to get big savings there. But it doesn't necessarily address the portability issue in the way that you're saying.
All right, thank you.
You're welcome.
So I was just curious. Can you actually also run this on Linux so that you can kind of do continuous integration and maybe deployment from a Linux build system to Windows application?
Okay, so you're trying to target Windows, but you're trying to build it on Linux. Probably not. I don't know.
Well, and just to clarify, the continuous integration being the generation of the projection is because, again, the artifact that this is just a header collection, a header library, pure header library. So what is it that you're imagining would be continuously integrated?
Possibly the projection, just kind of like the Microsoft header codes, and just both the consumer and the...
Sure. We do that already internally. We've got a TFS project that we have continuous integration turned on, and it's constantly rebuilding our compiler and then using it to generate projections. And so I could imagine something if you were, say, Win2D or some component author, and you wanted to make sure that every change to your interface definition would generate a corresponding projection without you having to lift your hands to do it, then you could do the same sort of thing. So sure, yeah, you could do that.
At the moment, though, the tools that we build and the libraries we've written, although it's standard C++, it's obviously Windows specific, and we're focused on that right now. I do have some enthusiastic volunteers at Microsoft, though, who are very concerned about cross-platform, and so we have a guy named Harry Pearson who's obsessed about this, and he's taken our code and our tools and he's ported all of it to Android. He has it running on a number of different platforms. So in that sense, this has been very successful, but that isn't our primary focus at this point.
Thank you.
You're welcome. All right. Well, if there's nothing else, thanks very much for coming.
Thanks.